Hello. So in this video I want to explain how we're going to obtain the Navier-Stokes equation from the equation of motion. Okay, so it will be titled from the equation of motion to the Navier-Stokes equation. And I'm going to divide this derivation in actually three parts. And so right here is the first part of the derivation. So first, I would like to remind you what's the equation of motion. So the equation of motion tells us that the partial derivative of the mass density times the velocity vector with respect to the time equals to the negative of the dot product between the nabla operator and phi here, which will represent our momentum flux, plus the mass density times the acceleration of gravity vector. Okay, so let me define each term. So rho here represents our mass density, and that's in kilogram per cubic meter. U will be our velocity vector. So each of these components is going to be expressed in meter per second. T is obviously the time, so this one doesn't need introduction, and it's in second. Here we have the dot product of the nabla operator and the momentum flux. So that's basically the divergence of the momentum flux. Okay, so this, you can also call that divergence. And in the Cartesian coordinate system, it's when you're deriving with respect to x, with respect to y, and with respect to z, which gives you this kind of units per meter. Phi here is our momentum flux, which is expressed in unit of mass per unit of length and per square second. So rho is our mass density, and finally we have our acceleration of gravity right here, which is in meter per square second, okay, in the SI units. Okay, so if we want to write that equation in, let's say, the Cartesian coordinate system x, y, z, which is probably the simplest way to write it, then we're going to have that's basically d over dt of what we have, our rho ux, rho uy, rho uz. That's rho times our velocity vector equals to the negative of our nabla operator times, or the dot product of the nabla operator, so the divergence basically of. So phi momentum flux, remember this is the second order tensor, that's a matrix. So we have 9 components: phi xx, phi xy, phi xz on the first row, and then on the second row we're going to have phi yx, phi yy, phi yz, and on the last row we'll have phi zz, phi zy, and phi, oh sorry, this one is 5zx, then 5zy, and finally 5zz, plus rho, and same, gravity is vector, although two of the components will be 0 here. We have gx, gy, and gz. Okay, so the first thing that we want to do is to use the expression of the combined momentum flux tensor. So we're going to take care of that particular term here. Okay, the momentum flux tensor. All right, so first step, use the expression of the combined momentum flux tensor. So what is that exactly? Basically, we can rewrite our momentum flux that we introduced there on top as a combination of several contributions, one that we will call pi, which will represent the molecular momentum flux tensor, and there is also a convective contribution to the momentum flux, which will be written as rho times the dyadic product of the velocity, like that. Okay, so let's define the terms. So this is actually the combined momentum flux. This is the molecular contribution to the momentum flux. So molecular momentum flux tensor, and this represents the convective momentum flux tensor. So by the way, here I should add tensor as well. Then we've seen, actually in the previous chapter when we talked about the Newton's law of viscosity, the generalization of the Newton's law of viscosity, that the molecular momentum flux tensor itself can be subdivided into two contributions. Phi equals to P delta, where P delta will actually represent the thermodynamic pressure forces, plus tau. So tau, that's also a tensor that represents the viscous forces. So let's again define each term. So this one represents thermodynamic pressure forces, and this guy here represents the viscous forces. And you got to be a little bit careful with also definitions. P here, so that's pressure. As you know, pressure is a scalar. It's a scalar field. And delta here represents the Kronecker delta. And in other words, just the identity tensor. And let's not forget our convective momentum flux tensor. Okay, plus rho u bar u bar. Okay, so we can try now to continue and see how it simplifies further. Okay. So we're there. We start again writing our equation of motion. Dou u over dt equals to negative divergence of our combined momentum flux plus rho g. Now we use our expression of the combined momentum flux tensor, which is going to give us negative delta or nabla, sorry, p delta. Then we also have negative divergence of tau, so contribution of the viscous forces, minus divergence of rho uu, and plus or rho g. Okay, so what we've done in this first step is we transform this into three contributions. Okay, now what I want to do next is look at this term here, which is the divergence of p delta. We're going to try to simplify it and see that it can be further simplified actually. So what is it exactly? We have divergence of p delta. If we try to write all the components in the Cartesian coordinate system, so again x, y, z, just to, for the sake of simplicity, to make the whole thing a little bit simpler to visualize and write also, then we know that the divergence is just derivative with respect to x, y, and z, right? So it's like you would have here d over dx, d over dy, d over dz. Okay, that's our vector field, and then we're going to multiply it by p. So p is just a scalar field, and that's multiplied by, sorry, the identity vector, where we have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so that represents the quanticle delta. Okay, so we can go further. So we have again our derivative with respect to the spatial coordinates. That just represents a one-line matrix, so a vector field. And that's a dot product of it with p 0, 0, 0, p 0, 0, 0, p. Okay, so that's the identity matrix here multiplied by p. And so after, basically, when you're a bit familiar with matrix calculus, so that's just basically going to give you a one-line vector, since you're going to have d over dx applied to p plus d over dy applied to 0 plus d over dz applied to 0. Okay, so that's going to give you at the end dp over dx. So that will be for the first column or the first row, depending on how basically you write your initial nabla operator. Then you have dp over dy, and finally dp over dz. So dp over dy arises from the multiplication of d over dy times p here, and dp over dz arises from the multiplication of d over dz times p on the last line, on the last row of our matrix. And that, I think you recognize that this is simply the nabla, or the special derivative of the pressure field. So in other words, our equation of motion really simplifies to d over dt equals to negative of the gradient of pressure minus the dot product of the nabla operator and tau minus the dot product again of the nabla operator and rho u bar, and plus rho g. Okay, so that's going to be the end of the first part, where we first looked into how to use the combined momentum flux tensor in our equation of motion. What we're going to do next is look at the time derivative on the left hand side of the equation, and that divergence of the dyadic product. We're going to say that they can be combined using what we call the substantial derivative. So that's in the second part of this little lecture.